Good afternoon, I'm Gloria Bordogna. I am a researcher of the National Research Council. Here I'm going to illustrate a soft computing approach that we have defined together with my colleagues here listed for mapping the status of the environment from remote sensing, mainly from optical remote sensing images within our institute, which is the Institute of Electromagnetic Sensing of the Environment. The motivation of the proposal can be summarized by the words of an Italian proverb: we do not want to throw the child with dirty water. In fact, nowadays, remote sensing data are big geodata that call for efficient and effective approaches to map the status of the environment in near real time, with periodicity, for example, for monitoring large areas. Ground truth data in the form of in situ observation and photo-interpreted data are generally scarce and sparse. But machine learning approaches are generally data-driven and need a large set of ground truth data for training, and the training phases can be long, and sometimes they must be repeated when changing the environmental conditions of the areas. On the other side, there is a lot of literature on remote sensing image analysis and interpretation that we could exploit for mapping the status of the environment, for example, for mapping burning areas, floods, vegetation covers, and so on. And there are many remote sensing experts, and we could represent their knowledge by means of fuzzy rule, and this is the idea. Nevertheless, soft computing is mainly knowledge-driven. It represents well ill-defined domain knowledge by means of fuzzy rules and fuzzy sets. It allows efficient implementation of near real-time solutions and provides transparent and human interpretable approaches that can be linguistically expressed and communicated to decision makers. But it needs mechanisms to adapt to local contexts, and it rarely provides adaptation mechanisms exploiting data, ground truth data. On the other side, machine learning is basically data-driven. It is very efficient to adapt to local contexts, but it needs huge ground truth data. It does not exploit available knowledge, and it provides opaque approaches which can be hardly summarized linguistically and communicated to non-experts. So our proposal is to combine soft computing with machine learning by designing a learning mechanism exploiting small ground truth data to define the aggregation operator of the fuzzy rules that encode the expert knowledge or the domain knowledge. Here is the schema of the proposed approach. The approach is a generalization of the workflow that is used by experts when interacting in a GIS in order to map the status of the environment with respect to a given phenomenon of interest. In the first step, they select data layers, which can be multispectral images or thematic layers that are named contributing factors, and apply selection conditions to segment partial evidence maps, which are binary maps of evidence of the phenomenon. In the second step, they aggregate these partial evidence maps by applying Boolean operators, the AND for the intersection and the OR for the union, in order to generate a synthetic environmental status indicator map. The generalization consists in replacing these selection conditions with a soft selection condition named soft constraints, admitting degrees of satisfaction, so that these partial evidence maps have spatial units that can assume values in 0, 1 in a real domain, expressing the different degree of possibility that the area may be interested by given status. And the Boolean operator are replaced by the ordered weighted averaging operators, which are a family of nonlinear mean-like fuzzy operators, whose behavior can be tuned flexibly between that of the fuzzy end and the fuzzy OR, the minimum and the maximum. The characteristic of such operator is that their definition can be learned from ground truth information, from small ground truth information. It is enough to have around 100 elements of observations in order to derive the aggregation operator. And this is what we perform in the second phase of the algorithm. Once it has been learned, based, for example, on in situ observation provided by volunteers or by photo interpreters, the aggregator is applied to the partial evidence map that are yielded by the first phase in order to produce the final environmental status indicator map. This approach can be efficiently implemented in a distributed processing framework, since it is based on 2 steps and since the activities is applied in each spatial unit of the image independently from the other spatial units. Each spatial unit can be a pixel, so the process can be pixel-based, or can be objects. For example, in the case in which we have boundaries of agronomic fields and we want to compute some status of the field. The first phase can be performed by mappers, which in parallel evaluate the soft constraint on chunks of the image, of the input images, while the reducers, in the second step, recombine the results of the chunks produced by the first phase on each chunk. The reducers also exploit ground truth information, here depicted as volunteer geographic information, in order to learn the aggregation for the given chunk. So, in each local area, in each chunk, we may learn a different aggregation operator, thus adapting the mapping to the local context. Now I'm going to discuss, to present a case study that we have recently published in the paper cited here, that is about the mapping of standing water areas from Sentinel-2 data. We consider 3 areas in northern Italy characterized by different environmental conditions. The first 2 areas treated by floods and due to heavy rainfalls, while the third area presenting controlled flooded rice paddies, in which the watered areas are shallow water with a depth of about 50 centimeters mixed with vegetation. So we wanted to test in different kind of standing water how our algorithm can perform. First activity was to select the domain knowledge. We selected 8 models, 7 of them computing different spectral indexes from optical images, and the last one using the color space H-view dimension of the color space. Then we engaged 2 different experts to define fuzzy segmentation thresholds on the spectral indexes map to generate gradual partial evidence maps for each spectral index and for each of the input model. These 2 experts engaged this activity by using a GIS in which they could analyze the distribution of classified data in the classes of flooded areas and not flooded areas, and so they defined this fuzzy segmentation threshold in order to best separate not flooded areas from the other areas. Then we designed a validation experiment based on k-fold cross validations that was aimed at computing the accuracy in the form of F1 score graphs to evaluate how the approach is robust with respect to the subjectivity of the expert knowledge and with respect of using small ground truth data. So the first phase was executed twice with the soft constraints of the 2 experts, and phase 2 was executed with 20 times, 10 times for the 10 cross validation in the typical setting when we use 90% of the pixel for training and 10% for testing, and the atypical setting for testing how is the performance, the accuracy when we have a small training set. To give you an idea, around 100 pixel classified pixel in each area. Here are the F-score diagrams in the when using the single models on the left, and when in our model for the 2 expert and in the typical and atypical validation. On the left you can see that there is not a unique model that is the best in the 3 areas. So which one do we have to choose for a new site? With our model, it is capable to select the best model in each area automatically. And the model, it is stable with respect to distinct experts, as you can see, and respect also to small ground truth data. It is superior or equal to the best model. A further result is the fact that we can represent the semantic of the ordered weighted averaging operator that has been learned in each area. For example, in the space of the dispersion and Hornes, on the right, you can see in the small rectangles that, for example, for Emilia area, we learned OWA operators which have a more democratic and less pessimistic semantic than in the other areas. This means that in this area, in order to better detect the standing water, we need a more synergic aggregation of the models with respect to the other area, in which we can use also a monarchical aggregation, meaning that we can consider the mapping of the most pessimistic, thus minimizing the false negative. These are the result of the final easy map averaged over the 10 runs of the typical setting when using small ground truth data for the learning of the aggregation for expert A and B. The average score over all runs and overall thresholds is high in all areas, above 89, and this reveals that our algorithm is very stable with respect to the expert knowledge and also with respect to the size. So to conclude, I can say that we designed a win-win solution with two levels of adaptation. It adapts to the rule aggregation in each local area by exploiting small ground truth data, and it is capable to select the most appropriate models, domain knowledge, in each spatial unit to determine a result. I thank you for your attention. The mathematical details are in the cited paper, and I will be happy to answer you if you send me emails.